rivers, mountains, along with the monitoring disasters, floods, droughts, and landform change. It provides a vast scope to explore identity and analyze the natural resources of the undeveloped region. It documents the dynamic changes in physical process and result in landform using the satellite images. As our first webinar session, we will look deep into the science concept behind the space imaging. It is conducted by Dr. Valikanna from Faculty of Geomatics in Sabra University of Sri Lanka. And he graduated at 2004 in Sabra University of Sri Lanka and did his MSc Geoinformatics, Department of Earth Observation Science, University of Twente, 2008, and did his PhD in Geoinformatics, Department of Civil and Earth Resource Engineering, Kyoto University, 2014. And I cordially invite our Sir Dr. Valikanna to conduct this session.
Okay, thank you, Anuba. Good evening, everybody, and I can see Janit and all participating from other countries as well. Welcome you all, and I don't know, maybe good morning, good evening, or night. Okay, so I welcome you all, and have to thank SEDS Sabra for conducting this. This has been an important topic a long time back. But at least because of the situation in the world, everything went online, so we had the chance to talk to you all. And it's a pleasure being here, and I cordially am really happy that there are almost like 170 participants right now listening to me. Let me start by giving you a descriptive dialogue on remote sensing first, and then we will look into what are the things that you have to discuss with me. This talk will be a little bit lengthy, but I know in a way it will be joyous as well. So can everybody see the screen that I'm sharing with you at the moment, the presentation? Anupa?
Yes, sir.
Okay.
Yes, sir, we can see.
Right? Yeah. Okay. So remote sensing is something that you have been listening and you have been heard, and some of you might have used. This talk is basically is the door to remote sensing, if I say, because I think I'm addressing a large amount of community. I know I have students who have worked under me in remote sensing, as well as some of you are really interested in remote sensing. That is really, really a good thing, and I'm really happy that you guys are interested in this subject. So may I start by asking, actually Anupa gave you a definition for remote sensing, something that you do without in physical touch with that particular object or phenomena. Now, if I ask you, you eat, you play, you swim, you sport, you climb, you track, and you do this in a discrete line. That means if I ask you every day that how many times did you eat? You ate only 3 times. But if I ask you what you've been doing for almost most of the time, unless until you are sleeping, you're doing remote sensing. Right? Everybody can hear me, right? Any problem with the sound? You can tell me, anybody, okay? So the thing is, actually, you do remote sensing day in, day out. You're doing remote sensing at the moment on me. You're watching me. You're listening to me. You're doing remote sensing. There is no time that you don't do remote sensing until you close your eyes, right? So this is actually a science that is more common to us, and we use day in, day out. But the thing is that I'm going to talk here is that a little bit away, because we do remote sensing from the ground or from our room. But now I'm talking about remote sensing from space. Why we do that? We want to look at where we live, the Earth. And if I ask you, do we know everything about Earth? No, we don't. Right? So my topic is why remote sensing, not what remote sensing. When I talk about why remote sensing, of course, I have to answer what is remote sensing. So it goes on, right? But the thing is, actually, we have to understand the potentials of remote sensing and the importance of remote sensing. So that's why I chose why remote sensing. So if I put you into this so if I put you some questions onto you, right, there are certain questions that are related to current crises as well as past things that we have been dealing on Earth. For instance, my first question is, where could be the COVID-19 hotspot in the sense of physical distancing, right? We want to know that because it is a crisis now. So if we go on measuring physical distancing on the ground and produce hotspots of COVID-19, that is going to take a long time. So there should be some other way as well. So the same way, if we are thinking of where the dengue and malaria is spreading, right, where our minerals are, right, and also where can we dump our garbage, where is deforestation is happening, right, and where can be our habitat, right? Where can we do our wind farm, where? All the question starts with where. So where, the question when it starts with where, right? Yeah, please others go on mute, yeah, because it's a lot of noise coming in, right? So all these questions start with where. When you say where, it's a position, right? It's a position on Earth. We want to know where. It's a position. We want to know a coordinate. So all these questions start with where, and it leads to a position on the surface of the Earth. So where the oil spills are, where can we find oil? Right? Where can we find urban hotspots and green spaces? Right? Where's the next drought going to hit? Right? Where can we have problems in agriculture? Like, for instance, you know, in Sri Lanka, there was the Sena attack, you know, the Sena pest came and attacked most of the agriculture farmlands. And it is quite a phenomena now in the central province as well. It's another pesticide, right? So agriculture is being affected by something, and we want to know the pattern before it gets out of hand. So if you're going to do it in ground, it's not going to happen, right? So we have to find another way to do that, right? And where do we have our historical places? And where do we have our endangered species? We know that there was a crisis with the black leopard, and we are losing that black leopard. If we can mark his boundaries, where he's actually hovering around, here his habitats and his behaviors in a way, without physically being in touch with that particular black leopard, that's the potential of remote sensing, right? That's the potential of remote sensing. So we go a little bit deep into this subject. I'll start a bit of history. You can see the history starting from 1839 when the first photograph was taken. It went on doing remote sensing for quite a bit of time, right? You can see during the World War aerial photogrammetry in 1920 to 1950. They wanted to know where the enemy hotspots are, and they cannot physically be there and get the information. They have to be away and get the information. So they needed remote sensing, right? And also you can see during the time in 1839 to 1990, people have been working in remote sensing tremendously, right? They have been sending photographs. They have been taking photographs from balloons starting, and from kites, and then from aeroplanes and airborne, and then they went to space. Now we are in the age of taking photographs from the space, If I call it a photograph, it's great, it's good, but actually it's not a simple photograph that we take from the space, because there is somebody out there in the space which we call satellites, and they take photographs, right? If I can go with a camera and do that, it's the same thing. We are doing remote sensing. So this is a bit of history. And if anybody is interested in having this presentation, of course, I am always ready to share with you this. Okay. So I will start with this satellite thing that we have to send up there, and it should not go alone. It should have capabilities. So the first thing that we talk about satellite-based remote sensing or monitoring something from the space, we have to talk about sensors. Sensors on board satellites. Satellite is the carrier, and there are instruments inside that, most probably an imaging instrument. So I'm talking about mainly in my talk today, imaging purpose satellites. Of course, I will give you hints of other type of satellites as well. So satellite sensors, mainly in the imaging domain, satellite can be segregated or classified into certain categories. You know, I'm talking about remote sensing, which is the imaging part of satellites. There are positioning satellites, you know, GNSS, GPS, GLONASS, Beidou, right? Those are positioning satellites. They don't take images, they give us positions. And there are weather satellites that predict storms, predict rain, predict wind, predict atmospheric differences, what is happening in the top atmosphere. Those satellites are also there. So classification can be done based on the purpose of the satellite. And also there are communication satellites. You know, Dr. Arthur C. Clarke from the University of Moldova, Chancellor of your University of Moldova, he invented the geostationary, I will come to this term, geostationary concept, where with 3 satellites, you can cover the whole globe, and you can use satellites for communication purposes. So the purpose changes what we send up there. So it's a huge amount of traffic up there, so much of satellites out there, and it's all based because we want to know our Earth much better. So sensors are on board, and sensors can be classified mainly into 2 types: passive sensors and active sensors. So passive, when it says passive, that means he's not actually working, he's depending on something else. What he depends on is the sun. Sun illuminates the Earth, and the satellite takes the energy that is being illuminated and re-radiated back to the satellite. So it's going to see what is happening on the surface of the Earth. That is basically what we do with the camera, right? We go and we take pictures and we use sun. If the sun is not there, we have to go for night modes, and we have to go for more wide angles and the apertures to take the light in the low light conditions. So we need lights, so passive, right? And there is another set of satellites that use active sensors. That means it doesn't depend on sun, it depends on by its own energy. So it sends its own energy to surface of the Earth, take it back and record it, right? So if I basically ask you which sensor you prefer in the night time from these 2, in the night time, which sensor you would like to prefer, which satellite you would like to prefer, satellite with passive sensors or satellite with active sensors? Of course, you have to use active sensors because you send your own energy. It doesn't matter whether it's there or not. Even in the night time, satellites do take pictures or do imaging, right? So the passive sensors and active sensors basically depend on the energy source, what type of energy source it is using, right? So and mainly passive sensors have certain drawbacks when compared to active sensors. Of course, active sensors also on the vice versa have problems with when you compare to passive sensors, right? I will talk about them when I show you all these active and passive images. Now, how these sensors do this? It's basically this, right? So the diagram that I'm showing here is a passive sensor, and it takes the energy coming from the sun, and it images and send the data to the ground station, and the ground station records the data, right? So it records the data, and you can see there is an active sensor here. Also, there is a passive sensor here. The passive sensor depends on the sun. Active sensor depends by itself, as you can see. So there is transmission, and there is illumination and re-radiation back to the satellite, recording and downloading the data from ground station, convert it into possibilities of usage. Now what you see is something like that. What you see, this image is actually taken by JAXA Advanced Near Infrared Radiometer Type 2. We call this Avenue 2. It's from Japan Aerospace Agency. One of the most comprehensive satellite series, ALOS. Quite useful, quite rigid, and can be used for a long period of time. So what you see is that image over Fukushima. You know very well this Fukushima, where the actually the catastrophe of tsunami came in and damaged the nuclear power plant. It's right there on the bay, right? So this was taken from the space looking at Fukushima, right? In 2011, somewhere around 2011. Now the satellite image is actually not like the image that we take from our cameras. We can see bright red, we can see bright cyan color, and also you can see dark colors as well. Most of you who have worked with satellite data do know what they represent, and I will talk about this a little bit later. So basically you can see I have shown the inner configuration of this image as band 2, band 3, band 4, right? And also I have drawn a line and said lambda. Lambda is the universal notation for wavelength. So this is something related to wavelength, right? These bands are related to wavelength. Just keep that idea right now. I will talk about it in length, right? And also you can see some matrices with numbers behind the satellite. Actually, this satellite is that numbers. Those numbers give us the capabilities to do image processing. And without those numbers, without those matrices, these images do not have any capabilities at all, right? So this is the whole process of remote sensing. Now you can see you don't touch anything, but you get an image of what is exactly happening down there. And the red color, mind you, is actually the vegetation. The cyan color is the urban areas, and the black color mostly is water, because everything is absorbed by water and there is no re-radiance back to the sensor. So basically, this is the setup. So there is a relationship between electromagnetic radiation and the image information. We look in deep a little bit. And how do this satellite do this? There should be internal geometry for a satellite to do that. So basically, the main components of satellite is that its own energy source, that is their solar panel. We cannot put batteries and send satellites because we expect a satellite to last for like 10 years. And also, if you think that when you send a satellite, it's going to go there and stay for a lifetime, it is not going to happen, because normally satellites are planned for like 10 years or maybe 15 years, maximum 20 years, right? It is very hard other than that, mainly because their own energy sources are fading away. And you can see two antennas. One is to transmit something, and the other one is to receive something. So the antenna theory is very powerful in this concept of satellites, and most of these antennas, the powerful antennas, keep developing, and the satellites are keep evolving. So you can see there are ground stations that control the satellite. It controls the satellite in its orbit as well as it's downloading the data. So ground stations are like remote controllers of satellites that actually know where the satellite and what it is doing and what health is it in. So everything is corresponded back to ground. And you can see in the second part, if I say the second column, you can see how these sensors scan Earth. The first, the top image, as you can see, the first top image, you can see that there is a sensor, and it is like scanning from left to right. It's kind of a mechanical scanner. So every time the satellite is moving, it just scans a line, and it moves a little bit further, it scans a line. And you might say, what if there is a gap between these two scan lines? Yes, of course, you're going to lose information, but it is not going to happen, because there is pulse repetition frequency that is actually set up so that the movement of the satellite is uniquely equal to the scanning size on the ground. So there will not be any gaps. It's actually always controlled by the ground. So I'm not going to talk deep in about pulse repetition frequencies. It's about geometry. If we talk about geometry, it's another topic. But basically, this is one of the geometry that is scanning. It is a mechanical scanning system. One disadvantage of this is that when you're moving something on always, it can get to wear and tear after some time. And also it needs a lot of energy. So basically, people try to find out a way that nothing is moving on the satellite. So then they move into something called push broom systems, where it's like a broom going along along underneath the satellite, and it sweeps away the terrain, and all the energy coming from that particular swath width, we call it swath, the swath width, from the instantaneous field of view. That means there is a cone of energy coming in, and whatever underneath that, it is being recorded in a set of cells. And you can see, if you combine those cells, you get a matrix of numbers. That's what I showed you in my previous slide. So these numbers represent the energy coming in. And of course, if I ask you, is all these numbers going to be same? No, never. Why? Because there are so much of differences in the land cover on the surface of the Earth. So whatever the energy it comes back to satellite depends basically on the wavelength the sensor is working on, and also depending on the surface structure, moisture, dielectric constant, and many other secondary parameters of the object itself. Energy coming from urban area is much larger than energy coming from water. So you can see, if I record the energy as a number, of course, urban area shows large numbers. Basically, I'm being very general. Urban area shows large numbers, while the water shows very small numbers because of the energy. If energy is inversely is proportional to the dn values we record. So dn, when I say dn, it is a digital number recorded in the satellite. All the images are made by these digital numbers. So these are the two systems that geometrically in satellite systems, passive satellite systems. Those are the passive satellite systems. That means it depends on the energy coming from the sun. Don't confuse yourself. Passive means I am not passive. Somebody else, right? Not me. So the satellite is not generating any source of energy. It depends on the energy coming from the sun. So that is passive. Active means I'm active. I'm sending my own energy. If you see the third column where I show you the microwave sensors, that is one of the most complex parts of remote sensing. You can see that its geometry of sweeping the Earth is a bit different from the second column, push broom and whisk broom, or the mechanical scan, right? So if you move on to these microwave sensors, you can see there is a slant geometry. And you can see that the satellite, what is shown by airplane is the satellite. Don't confuse yourself, because everything started from airborne, then it went up with the altitude, right? So consider this plane is a satellite. It's the same geometry. When it goes up, just the altitude is going up, right? It's still the slant geometry. And you can see in the passive sensors, you can see directly beneath the sensor on the ground, but in the active sensors, you can see you can't see the direct underneath area of the satellite. It sees somewhere else. So we say this off-nadir viewing. Off-nadir viewing comes in microwave sensors, while the nadir looking systems are almost passive. Right? So passive sensors and active sensors, depending on their capabilities of recording energy, changes its geometry. I hope you understand the slight configuration difference in the scanning geometry of these active and passive systems, right? So main difference, active sensors can't see beneath them. On the nadir, there is no nadir look, but for active sensors, always there is nadir look. So if I move on a little bit to the DN values, as you can see, this image is actually Sentinel-2. I will tell you what is Sentinel-2. I'll be using some of the terms, but I will come back to what they are in a bit of time. So this is European Space Agency Sentinel-2 over Bere Lake in Sri Lanka, right? And what I have done is I have taken all the DN values and I have plotted that in an in-dimensional visualization. I'm sorry that I'm not going to play videos, otherwise you would have seen this is a cluster moving. It's n-dimensional, it is not three-dimensional. Why? I will tell you in a while. You can see 1, 2, 3, 4, 5, 6, 7, 8 axes in this. And why is that? I will tell you in a while, right? And also, if you can see the distribution of these pixels, where the pixels are getting lower values, where the pixels are getting higher values can be seen, right? You can see them. So basically, and also here in the histogram, you can see there are a number of distributions. So I told you that there are 8 axes, and for 8 axes, you have 1, 2, 3, 4, 5, 6, 7, 8 histograms, right? Now, I'm getting several questions. I will answer them in a while, okay? Right, in the chat, I'm getting questions. I will go on and I will answer it, okay? So you can see there are 8 histograms for 8 bands. That means this particular image, what you see, is not a single image. It's a combination of 8 images. What do you mean by 8 images? 8 regions of the electromagnetic spectrum. So 8 regions in the electromagnetic spectrum, you get 8 images, and those 8 images have 8 different DN values depending on the energy coming in, and they are being plotted. So you can see the difference. And also some of the students who learned statistics from me, I always stress the fact that most of these natural phenomena follows the Gaussian distribution. As you can see in the histogram, this is a Gaussian distribution. The pixel distribution of the satellite data normally are Gaussian or normal distribution. There is a mean value and the variance, right? So the best distribution that describes the pixel values in a satellite image is normal distribution. Of course, it changes to active sensors. Sometimes it goes to gamma distribution or circular Gaussian distribution. It goes on when you go deep into remote sensing. So the reflectance is there in different bands, and also the pixel distribution is there, and you can see the cluster of pixels as well. So this Sentinel-2, I see a question saying free Landsat data. Of course, I'm going to talk about Landsat in a while. Sentinel-2 is also free. Landsat is from NASA, Sentinel is from European Space Agency. ESA means European Space Agency. I go a little bit further, right? So now what is happening actually? I talk about energy being recorded by a sensor on the space, and what is happening actually there in the physical sense. Something is coming, hitting the target and going back, and I'm trying to record that. So it's not like I'm taking a picture of my friend who's close by. I can take that picture very well because he's very close to me and I can get a good picture of it. But the problem is these satellites are on top of atmosphere, and atmosphere is like 300 kilometers and various things are happening in the atmosphere. So on top of atmosphere where the satellite is standing, or his office is there, from his office, it's very difficult for him to see the ground because there is atmosphere playing all the tricks. So we have to understand when we are capturing remote sensing images to deal with this atmosphere. That is a very deep scientific part. And mind you, there are so many PhDs working in the region of atmospheric modeling for remote sensing image capture, right? Atmosphere is a very complex area, very mathematical area, but basically what I'm saying is that irradiance from the sun, we call it irradiance. It hits the ground on an object and re-radiate back. So the radiance is going back to the sensor. So what is spectral irradiance? It's the power density across the wavelength. So it's actually the power, watts per meter squared for micrometers. A single unit wavelength for unit area, what is the power coming from the target, right? That is spectral radiance. So the radiance is actually the joules, that means the watts per meters or joules, the amount of power density scattered back in a particular direction. So when something is hitting the target and going back, it can go in any direction, but we consider it is going in a cone way, in a particular angle. So we put watts per meter squared per steradian, that means for unit angle, how much of power coming back to the satellite. So I'm not going to deeply explain about these power concepts. You will learn if you're going on studying remote sensing deeply. You have to study about these radiance, irradiance, and the reflectance. Reflectance is the amount of light leaving the target to the amount of light that hit the target. So it hits some amount, absorb, get scattered away, and something going back. So remember, when something hit, the light hits the target, all of that is not going to go back, right? Something is going to get missed. So there is a ratio. So that is called reflectance, right? So reflectance is the important thing that we record from satellite. So we call it radiance to reflectance conversion, and it comes under atmospheric corrections in remote sensing, separate area. So we take the reflectance. Now, reflectance properties of objects depend on their nature, and that is very important for us, right? So if there is a rock, its reflectance property is completely different from a tree, right? Something hitting and something going back, right? So their reflectance is a ratio. It's a division, right? Now, when we talk about the science of capturing, we have to talk about where the satellite is actually orbiting, right? There are different type of satellites. You know that Sri Lanka is also having a satellite on top of us. I don't know which orbit it is in, right? So we know about the orbits of the satellites, basically. Now, there are three types of orbits: polar orbits or non-polar orbits, we call sometimes, low Earth orbits, and geostationary orbits. Previously, it was polar orbits and geostationary orbits. Now that there is a second one coming in, non-Earth, low Earth orbits. Now, these polar orbits are the orbits that we occupy mostly in imaging science, because the satellite is, you can see in the first image, is somewhere like from equator, it is more than 90 degrees, so that there is a little bit of slant with respect to the poles. So the satellite is slanted and it reaches the poles, not directly on top of the poles, but very close to the poles, and it goes on. So the satellite is like near polar orbits. It goes, it travels, and the Earth is rotating. So the satellite is not going to change its orbit. It stays in its orbit, and the Earth is rotating. So we can get continuous strips imaging the whole Earth. Hope you understand. So we call these polar or non-polar orbits, right? And then low Earth orbits. So there are many imaging satellites that occupy polar orbit, but when it comes to non-polar or low Earth orbits, one of the most famous thing in low Earth orbit is the International Space Station. It is somewhere like 400 kilometers. So it is not actually like moving like a satellite, not that fast, but it is there, right? It is not going to fall. It's not going to go away from Earth's gravity. It's going to go stay there. So we call these low Earth orbits. So the there are some other satellites like global precipitation measurement satellites that are satellites that track the hurricanes, tornadoes, and go on top of them and image them, so they can't be in a very high altitude. It should be in the middle altitude so that it can track hurricanes. You have seen in the news, especially in NASA images, you have seen Hurricane Katrina. You can see the hurricanes, how they track them, how they get the eye, how they go and on top of the hurricanes and picture. I will come to that in one of the slides. I have dedicated to that. So these are low Earth orbit satellites. Especially they are dedicated to the International Space Station, one of the thing, and the other one is actually the meteorology satellites that detect weather. And also geostationary satellites, mostly communication satellites, stays with Earth and rotates the same way. So every time it's nadir is the same thing. So if we have a satellite on top of Colombo, always that satellite's nadir point, that means directly underneath point is Colombo, right? So it always move with the same speed with the Earth, and therefore it always see the same path, but you can see a large area, right? So I believe that whatever the satellite that we have since should be a geostationary satellite. It is on top of us, and we don't have the capabilities of acquiring polar orbit satellites because they are actually advanced science and advanced engineering, and I don't think that we have that kind of engineering with us. So these are the three satellite orbits. You can ask about those satellite orbits in our discussion. I just move on. And this is one of the most important slides in my whole talk, the electromagnetic radiation generated by the Earth's surface. And you can see there is a satellite and Earth is there. And the whole range of electromagnetic spectrum is there. And you can see the wave, right? So the longer wavelengths, you know that when C equals F lambda, so frequency into wavelength is a constant. So when two things are multiplied together, and it should be, it has to be constant always. One goes up, then the other should go down. So longer wavelengths means lower frequencies, larger wavelengths means lower frequencies, high frequencies means lower wavelengths. You can see that in this figure. So long wavelengths in the region of radio window, you can see this radio window is there, optical window is there, and there is places that has opacity. That means there is nothing going from those regions, right? But there are regions where windows are there. It's like you open the atmosphere for that region, so the electromagnetic radiation goes back to the satellite. But other regions, the door is closed, so we call them atmospheric windows. So whole electromagnetic spectrum, you can see how the atmosphere plays its part. Some parts atmosphere block, some parts atmosphere doesn't block. So all remote sensing imaging satellites work on these regions where the atmosphere is opening its doors. So you can see there is radio window, optical window. Those are the areas mostly remote sensing is happening. So the opaque areas, we don't have any sensors working on. We can't see the electromagnetic energy coming from those regions from the surface of the Earth because atmosphere completely blocks them and you can't see it from the space. In that case, we have to come down from the atmosphere and go air, right? We can't go spaceborne. So you can see the visible light, that is actually humans, that is most famously known as red, green, and blue, right? So visible spectrum is very small, you can see, right? That is what we as humans, we can only see these regions. So from a whole electromagnetic spectrum, you can see visible light is very small region. And most of the satellite images that I've shown up to now, right, you saw they have land cover information. They work in the visible region, but they have a lot of limitation because it's a very small area. It's a very small area, right? And so, but we take the advantage of that. There are many number of satellites working on this optical window, right? There are many number of satellites working in this optical window. Also, there are many number of satellites working in this radio window. I will talk about this radio window and the optical satellites in the optical window. Namely, because there is optical window, satellites working on this optical window are called optical satellites. They are sometimes called multispectral satellites, optical satellites. And the satellites working in the radio window are called radio wave satellites, microwave satellites, right? So basic difference, visible range satellites occupy short wavelength electromagnetic radiation. You can see at the optical window, the wavelength is getting smaller. At the radio window, the wavelength is getting larger. So the radio waves, or the very well-known synthetic aperture radar, works in the radio region, radio window region, and they occupy longer wavelengths. And in the optical region, the wavelength is small, so it occupies those region and create images. Mostly, the satellites in the visible region or the optical window are passive systems, and satellites in the radio window or the satellites working on the microwave region, they are active systems, right? They need their own energy, right? So this is very important part of the remote sensing understanding. You have to know the wave theory, and I have shown you some the waves, how the lambda is different for different waves, and there is another wave that shows electric component and the magnetic component perpendicular to each other. I will show you images generated by those kind of waves in the end of my talk, right? So this is very important key figure in my talk, right? So you can see how we occupy electromagnetic radiation for our purposes in the ground other than satellite imaging. Down there you can see, right? Okay, so when this electromagnetic radiation is being recorded by the satellite, it's different for different objects on the ground. Now I have an identity card, and if I show my national identity card, that's me. And if somebody else shows his national identity card, he himself is somebody else. The ID number is different for me and the other person. The same way, depending on the energy reflected back to the sensor by objects, they generate a signature. We call this the spectral signature. Mostly the spectral signature is generated in the regions of visible range, right? As you can see, 400 nanometers to 800 nanometers, that is almost the visible range, right? In the wavelength in nanometers. So in the visible range, they behave in a way. So if the energy is coming from a vegetation patch, if the energy is coming from a water patch, if the energy is coming from a soil patch, if the energy is coming from some other places, it tends to behave differently in different wavelengths. My personal view of remote sensing, the main parameter of remote sensing is lambda, wavelength. Wavelength do everything. Wavelength is the fundamental property of remote sensing. Now you can see the wavelength is changing from 400 meters to 800 meters here, right? So, sorry. So it changes from 400 meters to 800 meters, and you can see there is turbid water. Their reflectance is very poor. It's almost a straight line. Clear water, even poorer, right? It has only a signature near 400 nanometers. At 800 nanometers, it is almost like zero, the percent reflectance, right? And soil, of course, they are better than water. They have high spectral irradiance. That means more energy is coming from dry soil and wet soil. Of course, wet soil, its moisture, because of its moisture, most of the electromagnetic radiation is absorbed and partly gone back. So, of course, its spectral signature should be lower than the dry soil, right? And also, you can see the vegetation. It has the most beautiful pattern. We call this the red edge, and it behaves in a very different manner than all the other things. So, basically, there are a lot of applications in vegetation from remote sensing satellite data. And snow and cloud, they are on top. They have high albedo. Albedo is a term that you have to know if you're doing remote sensing. How much the surface reflect light instead of absorbing. If the albedo is high, we care 90% of albedo. Snow reflects a lot of energy. Of course, water does not reflect a lot of energy. So oceans have low albedo, snow has high albedo, mirrors have high albedo, concrete has high albedo, but when it comes to dry, wet soil and moisture soil, they have low albedo. So the albedo is something that you have to know, the amount of the amount of light being reflected back without getting absorbed. So this spectral signature, as you can see in this diagram, is different for different features and objects on the ground. So we call them fingerprint of the objects, or we call sometimes the spectral signature. Remember the term spectral signature. We use spectral signature from the remote sensing images. We generate the spectral signature from these remote sensing images, and we can get the spectral signature on the ground, and we map them, and then we can see what objects are there on the image. This is how we do mineral mapping. So the overall setup what I have been talking is here. You can refer to this diagram. As you can see, the geostationary satellite, Landsat and Spot, and then the space shuttles and high altitude jet planes and low middle altitude airplanes and the ground, right? And the wavelength is also there, and you can see the energy is coming and hitting the Earth's surface and going back. This is the basic property of remote sensing. So there are few more keywords that you have to know in order to understand the basic things of remote sensing. It's the resolution. Resolution is a parameter inherent to satellite images. There are mainly 4 types of resolutions. One is radiometric resolution, spatial resolution, spectral resolution, and temporal resolution. I'm not going to read this, but if I ask you, if I give you 4 colors and 10 colors to draw a picture on a scenery, you have the feasibility of 4 colors in the first place, and you have a feasibility of 10 colors in the second place. So which picture will give you more information? The one you are going to use more colors, right? Of course, with 4 colors, sometimes you don't have green, so you have to paint the trees in the same color as water maybe. So water and tree both have blue because you don't have green there. Understand what I'm saying? I hope you understand, right? So, but if I have 10 colors, of course, I have green for trees, the brown for soil, blue for water, light blue for the sky, orange color for the sun. So I can depict the picture much more detailed. So we call this radiometric resolution. Number of gray levels in the first picture is 4, the second picture is 10. More details are there in 10, less details are in 4 because it is generalized. More, you don't have the feasibility of using different type of colors, so you tend to use general color. So what you see in this image is that the first one is actually 2-bit, that means like 4 values, 4 colors, and the second one is 16 bits, 2 to the power 4, right? So 16, so it's like 16 color types you have, and the third one is 8-bit, 256, because 2 to the power 8 is 256, 0 to 255 values, 0 is black, 0 is black, and 255 is white. So you can see some of the information which you don't have in the first picture is there in the third picture. So the radiometric resolution is going higher. The number of gray levels that you have, number of DN numbers you can use to record the third image is much more larger than the first image. When you go to spatial resolution, you know this term very well. It's the smallest area that you can see on the ground from a satellite, and if the smallest area that you can see on the ground is like 2 centimeters from one satellite and 30 centimeters from the other satellites, of course you can see something which is much more larger than 2 meters will have 2 pixels in the first image, while something much more larger than 2 meters will have only 1 pixel in the 30-meter resolution image. So in the first image you can separate this object, but the 30-meter image you cannot separate that because it is inside a pixel, only 1 DN value, right? So when the spatial resolution is getting higher, we say high spatial resolution, that means low value, that means like 1 meter or 2 meter or 0.6 centimeters. That is very high resolution. You can see a 0.6 centimeter, 0.6 centimeter area on the satellite image. That means 0.6 centimeter, 6 centimeter means if me and another person stand 0.6 centimeters away, there you can count there are 2 dots in the image. Basically, you can count the number of people, right? But if it is 30 meter spatial resolution, both us are in 1 pixel, so there is no 2 points in that case, right? So this is the spatial resolution. So that's why we sometimes when we do projects, people ask, I need high resolution. What do you mean by that? You need more details on the ground. You need a small resolution, a small pixel size. Some says, okay, I'm fine with lower resolution, 30 meter, because he's doing a study on forest. He doesn't want to count the number of trees, right? So it's okay for 30 meters, right? Likewise, so the spatial resolution define high resolution as well as low resolution. Most of you know about spatial resolution, right? Spectral resolution, the third one, is how these features are represented along the electromagnetic spectrum. Just imagine if I can get 4 regions of the electromagnetic spectrum recorded, I will have 4 images. One in red range, one in green range, one is blue, and one in near infrared range. So I will have 4 images. So of course, objects will be different in red region because the amount of energy reflected back is different. Green region, it is different. Blue region, it is different. Near infrared region, it is different. So some of the objects which are not represented in the blue region will be there in the red region, because in the blue region the object absorbs all the energy, but in the near infrared region it reflects. So in the near infrared image you can see the object, but in the blue you can't see, right? So just imagine if I have a large number of bands, large number of areas of the electromagnetic spectrum being imaged, what can I see? I can see a lot of details, That is what is shown by this cube. This is not just an exaggeration of the image by blurring or something. This is number of bands recorded by the satellite. That means each narrow region of the spectral electromagnetic spectrum, each narrow region of the electromagnetic spectrum has its own image. So sometimes we call these remote sensing hyperspectral remote sensing. Not sometimes, we call this hyperspectral remote sensing. In hyperspectral remote sensing, you have like 196 bands, 225 bands, right? As I have shown here is a Hyperion image, which is a hyperspectral image from one of my research papers. As you can see, the spectral signature is very continuous, right? On top of vegetation, the red color is vegetation. You can see the spectral signature is very continuous. But remember, previously in a slide, I showed a spectral signature, which is like very linear lines going down and there. That is not continuous. This is very continuous, right? This is on top of the Forest Research Institute of Dehradun, India, taken from Earth Observation 1 Hyperion satellite. And it has 225 bands. Out of 225 bands, you can use 196 bands, and this is a combination of 196 bands. So just imagine the amount of spectral information that you have in a hyperspectral remote sensing. Remember, spectral info resolution is very high for hyperspectral remote sensing images. I will just quicken up. It's almost like 1 hour. Maybe you guys might be going boring. Some of you might not be there, right? And you just hang on. The temporal resolution is that, you know, the satellite is going in an orbit, so it can't be the same place unless until it is geostationary. So it has to go and come back to the same place. How much of time that it will take to come to the same place? So normally all the satellites, imaging satellites in polar orbits, cross the equator around 10:30 p.m. in the morning. So most of our images over Sri Lanka are in the morning time, right? So we have to wait till the satellite comes to Sri Lanka after after the Earth rotates and come back to the same place. So mostly like Landsat and Sentinel, it captures the same place. It goes to the same place after 16 days. So we call the temporal resolution is 16 days. So when I say temporal resolution is 16 days, that means for 16 days, if something has happened between these 16 days, there is no image for that. Okay, you have to wait. So for 1 month, there will be only 2 images in Landsat over Sri Lanka, over America, over Kyoto, Japan, over Melbourne, Australia, right? Only 1 image, only 2 images per month, 16 days, almost 2 images. So if anything happened between that 16 days, there will be problems. In that case, what we are going to do, there are things we can do. We talk about it some other time, right? So, okay, I'll move on. Right, so these are the satellites that we normally occupy, and this is one of the greatest satellites is Landsat, always free, and have contributed immensely to the development of remote sensing. I have used Landsat for a long period of time, more than like almost like 20 years of my career. I've been using Landsat from the 7, Landsat from 5 to now 8, and it is all free. Why it is called Landsat is that it land imaging the land. That's why the satellite imaging the land, Landsat. And actually, this particular island in Canada, it is called Landsat Island. It was given that name because the island was found by an image from Landsat. So it was given. So it has 9 spectral bands, 9 spectral resolutions, 2 spectral bands in thermal infrared region. That means measuring the heat or the emissivity, the temperature of the land surface, and 16-bit resolution. When I say 16-bit, it is 2 to the power 16 gray levels, so more amount of details. It's not the 2 to the power 8 or 2 to the power 4. It's 2 to the power 16 DN values, large variation of gray levels. You can show a lot of information. Sentinel is from ESA, Landsat is from NASA, Terra is also from NASA. Now it's no more in the operation. Earth observation 1, which I showed, is Hyperion in my previous slide, is from this satellite. It's a hyperspectral satellite sensor. And the world view, these are high resolution satellite. If you can see how many of containers in this yard can be counted from this satellite. World view is very high resolution. It is 31 centimeters, so you can count. But in Landsat, you will not see this count because it is 30 meter, 30 meter. For 30 meter, 30 meter area, most of these containers will have only 1 DN value, so you won't see, right, separation. So this is 31 centimeter. World view is very high resolution, and it is not open source, so you have to purchase it, very costly. World view 1 failed, and World view 2 went up there, and it is called World. And also spot satellites from France. It started from spot 1 and it went to spot 3, spot 2, and then the line was actually disaggregated or discontinued, and then now it is back in the track with spot 5, 6, 7 with 10 meter to 6 meter resolution. It is from France, and it is very good, very nice images. RadarSat is actually a microwave sensor, active sensor. It doesn't work on the visible region. It works on the microwave window or radio window. Now it is no more in in performance, but it has also contributed heavily to the development of remote sensing. Iconos, you know very well, it's also a high resolution satellite. QuickBird is another high resolution satellite of 6 centimeters, mostly used in Google Earth images. QuickBird has an agreement with Google Earth, so most of the Google Earth images are coming from QuickBird. ResourceSat is from Indian Space Research Organization, very useful satellite images, not very expensive, but very good. And you can do a lot of work from these ResourceSats as well, or Indian remote sensing IRS satellites, in IRS or Indian remote sensing satellites from ISRO, Indian Space Research Organization. Okay, and also RapidEye, another constellation of satellites. SEDS from France, Cartosat from India, Joe-I from Digital Globe, USA, and Advanced Land Observation Satellite from JAXA, Japan. Okay? Those are the satellites. So I have been talking about this window. Now I will show you once again the atmospheric windows. And this is the constellation of NASA satellites at the moment. There are more, and one is SRTA. It's a shuttle radar topographic mission. It uses radio waves to map the topography of the Earth. It gives digital elevation models. It doesn't give images. It talks about the surface or the elevation of the Earth. So there are terms in remote sensing depending on the sensors, and you can read about these. These are more or less all the sensor types that is being uploaded into the payload of the satellite, and these are the instruments that we use in order to image the surface of the Earth. When I say image the surface of the Earth, people have moved from taking just a photograph to measure the length from the satellite to the ground and any difference between satellite to the ground. All that people are doing. Three more important remote sensing projects from NASA. One is Global Precipitation Measurement Mission, GPM. Just be aware of this mission. You can visit this site. I have given the reference in the last slide, and you can visit this site and read. And basically, this is a radar satellite, and you can see it goes on top of it. It's in the low orbits. It goes, it tracks the hurricanes, and it measures the distance from the satellite to the hurricane top and the bottom, so it can calculate the volume as well as it take the image of the hurricane. So then what happened, we can make three-dimensional information about rainfall, how much of rainfall is there. You can see what type of information we can get. So these satellites are weather satellites, and this mission has been transferred from Tropical Rainstorm Mission, TRMMM. Now it is turned into Global Precipitation Measurement Mission. It's not only NASA, now ESA, JAXA all contributes to this, right? Previously it was NASA project. Second one is very nice one, very recently sent satellite. I think you might have got to know about this in 2019, early last year. It measures the 3D wind shield of the Earth's surface. Very nice way. It sends a LiDAR pulse, that means light wave, and it hits the atmospheric winds and scatters back. So depending on the scattering, the amount of energy changes. So basically there is a mechanism. As you can see, the strength of the signal is measured, so you can get an idea of this wind strength, right? So this is called ALOS. It's actually a Greek word coming from poet Homer, that is the keeper of the control of the winds. That is the name given to the satellite, not like the names that we give in Sri Lanka for some of the projects, people's name, right? There is a meaning when they give a satellite a name, right? So these are the two instruments inside this. And the last one is GRACE, Gravity Recovery and Climate Experiment, GRACE mission, which observed the gravity anomaly of the Earth's surface. So basically the anomaly, how the gravity is changing on the surface, or because of the internal changes of the volume and the cluster changes, is being monitored. Now in this mission, it is completely different concept. Please read about this. What it happened is that there is twin satellites, and it moves on, and it keeps a continuous distance between them. It can measure the distance between them, and when they are moving, depending on the gravity of the surface of the depending on the gravity of the Earth, sometimes their distance is changing. If there is a high gravity, it's like this. If there is high gravity, the satellite moves slower. The other one is in a low gravity region, so it moves faster, so the distance is getting higher. And if the gravity is both, the satellites are influenced by the same gravity, they keep constant distance. So they measure this distance and convert that into gravity. So there is nothing like reflectance coming from the surface of the Earth for GRACE, the gravity recovery mission, and they can create the gravity anomaly. And I have given how they can convert these gravity anomalies into radicals, and also the relationship between square second to meter, or the acceleration, depending on the gravity. Okay, so these are the three missions that you have to be interested in. The current missions the NASA is providing, and you can read about their dedicated pages. You can read a lot, and you can understand once you understand the basic concepts of the remote sensing. This is Colombo, and I said different bands, and this is a Landsat 8 false color 2019 628 over the port of Colombo, and you can see there are 7 bands I have aggregated and created this false color image. We say false color because we put the computer gives us an image from using RGB components. Only 3 channels are there, so we can put near infrared into R, green into green, and blue into blue. In that case, we sometimes call it false color because we are manipulating the colors. So in this case, I have given bands 4 to the R band and 6 to the green band and 7 to the blue band. So this image is produced, and you can see how much of cloud cover is there, and also the red region mostly is vegetation, and you can see soil, and you can see the port as well. And if you look at these bands, they are performed in different wavelengths, and their information is different. 16-bit resolution. Now, some of the bands you can see in the band 7, it is the soil is not performing good reflectance. Of course, in the near infrared regions, soil is not performing very well, but vegetation is performing more because the spectral signature, as I said earlier, the reflectance curve is different in these regions. This is a Landsat 8 mosaic. That means I have combined several images in order to make this whole map of Sri Lanka, and you can see how the satellite is moving. That's why I put this picture. You can see the polar orbit now here, the polar orbit and the swath. So there is one swath going one orbit and acquiring the images, and after 16 days the second one was not after 16 days, the next day, when the earth is rotating, it has occupied the second strip, and this is actually ascending path. That means going from south to north, and the third one is also an ascending path. But you can see they are almost like, when I say that this is same day, it has slight differences. You can see in the strip 2 and strip 3 there is difference of clouds, and you can see that it is not being taken at the same moment. So this is how the satellites are moved, and satellite images are mosaic. When we call this mosaic, it's a combination of all the tiles together. And the map information is also there. So this data is spatial data set. You can it's given by RPC coefficients of the orbital files. So the satellite image is having a georeferenced coordinate system. You can transform or project this coordinate system into this is in geographic latitude and longitude. The datum is WGS84, and you can convert this into projected coordinate system meters. This is Sentinel-2 over Colombo. And between 2016 and 2019, you can see how the port of Colombo has been changed during this time. And of course, the cloud cover is coming up. This is, I put this because there is a current project that I'm working on to see how the Mount Lavinia coastal zone is being changed for a certain amount of time. So we have to, just by taking the image, we can't do that. There is a significant amount of processing that is needed in order to identify the shoreline properly from the satellite image and generate it into a time series and see how the shoreline is changing, right? So this is actually the coastal zone. One thing I wanted to show you is that there is a landmass came up here, which was not there, the port city, and after it was constructed, you can see the water currents might have changed in this region, and the first curve is actually the Mount Lavinia beach, and most of the currents directly may have hit this region and made a significant amount of coastal erosion, which I'm trying to detect from Sentinel-2 false color composite of 2016 to 2019. This is a thermal image. This doesn't show the reflectance, it shows the emissivity. That means basically the temperature of the of Colombo region. So this is from Landsat band 10 and band 11. Converting these DN values into brightness temperature is done by some equations. I'm not going to talk about that equation, but most of these radar images doesn't come like this. We have to process them and take them to the place where we can use them. So this is how it is being converted into land surface temperature. So we have used band 11 and band 10 and 11 of Landsat 8, and Landsat has the capability of thermal emissivity detection. That means the heat coming from the surface of the Earth, but Sentinel doesn't have these thermal capabilities. This is a WorldView 2 image, which is showing a landslide in Koslanda, happened in 2016. And you can see this area was quite stable. And after that, there was a huge landslide. This Koslanda landslide made a huge disaster in this region. And there was a lot of catastrophe in this region because of this landslide. And it was marked as a signature in WorldView 2. Separate part of remote sensing is reef remote sensing. So we used data in order to understand subwater features like coral reefs, and these are the main coral reef regions of Sri Lanka: Bar Reef in Putlam, Gaul and Rumasala Reef in the south, and also the Pigeon Island, which is somewhere here close to Trincomalee. Right, so we can detect what is happening to our coral reefs. As you can see, there is a lot of spectral information in these images, even underneath the water, especially if we can use several bands like blue band, and there is another band in Landsat 8 called coastal band, working in close to the blue region. There is a probability of feasibility that we can get a penetration from the water, and the energy is going to reach the coral reef, so we can identify or understand if there is coral reefs breaching or dying. So separate part of remote sensing are now termed as reef remote sensing, and techniques are different because we have to work underwater, and it's a bit difficult, tricky, and a lot of mathematical modeling is involved in this to extract what is down there from underneath 1 meter or 2 meter water penetration depths. So it has been developed now. Normally we use satellite data for reef remote sensing as well. This image I just want to show you. This is Colombo Metropolitan before the COVID 2020 lockdown in 2019 12/27, and this is after the lockdown, right, from Sentinel-2 images over Colombo. And this is actually change image between these two, what happened in this area, what land covers has changed, taking a ratio based change detection method. And you can see the red areas have changed mostly if you consider and if you look at them, their vegetation, because the activity of humans have been realized and gone really minute, and because of that the vegetation has been going very fast. All right, last part of my talk, very few minutes. I'm moving a little bit to microwave remote sensing. I said it is not a nadir looking image, it's an off nadir looking image and works with longer wavelengths. When there is longer wavelengths like 1 meter or 2 meter from the satellite hitting the ground, of course if we know the number of pulses, if the wavelength is like 2.5 meters, say for instance, multiplied by the number of pulses, we can measure the distance from the satellite to the ground. Yeah, so microwaves are long wavelengths. So if we use them, of course, we can detect the range, and we can know where actually the land surface is. If the land surface goes down or up, yeah, of course, the distance from the satellite to that spot is going to change. And if there is a subsidence, or if there's an earth slip, or if there is a landslide where the topography is going to change, of course, this distance is going to change. So some mechanism is different in microwave regions. And also microwave can come or out of cloud and hit the ground. It doesn't have cloud cover. It can take images day or night. Heavy rains doesn't matter. Heavy canopy, sometimes across the canopy it hits. And most of you now listening to me are surveyors, and you know that the GNSS or the GPS uses radio waves. Just the same way, for imaging purposes, we use radio waves in synthetic aperture radar. Right? So both GNSS uses wavelengths of in the region of microwave. So because of that, we can do measurements as well from satellite to the ground or the object. And also, when you're using these longer wavelengths, you have to consider which plane this wave is moving. Is it moving in the horizontal plane or the vertical plane, right? So waves in the microwave region can come vertical plane and go back horizontal plane, or vertical plane and go back vertical plane, right? So in the microwave imaging systems, we don't have bands, we have polarizations. Okay, these are getting a little bit trickier, but just remember this general talk. This is complete different subject area, but my remote sensing. So these are the Sentinel-1 C-band synthetic aperture radar over Sri Lanka. The original image is not very pleasant. It's ridiculous, if you can see. Sri Lanka has gone from west to east, right? But you have to do certain amount of processing in order to get that. And one thing you can see, there is no cloud cover. There is no cloud cover in these images. And what I am trying to do is actually these images were taken during the time in Colombo floods when there was heavy cloud cover. And if I take optical images, you can't see anything about Colombo. It's all clouds. But those days I took the radar images and I generated the flood signature along the Kalani River basin. So this is the flood that had happened in Colombo way back in 2019, 2018 or 2019, in the beginning of 2019. If you can remember, there was a heavy flood in Kaduela, Colombo region along the basins of Kalani. And also we extended these to the northern floods of Kilinochchi area. And you can see we have generated the water areas, because microwave has the capability of giving us images during these kind of catastrophic times, like heavy rains. And of course, if we can take a past image and the present image after the flooding, the changes should be water, right? That is what the basic concept. So you can see I have uploaded, or I have tried to figure out where the flooding has happened, and most of this flooding has happened in the areas where there is lagoons and paddy fields. And this was actually given to the Agriculture Department of Sri Lanka upon their request, processed by synthetic aperture radar, not optical images, because these days you can't find any of the optical images. This is another set of work that we are working on currently. We are trying to figure out where the areas in the central province is going to get subsided. So we use single loop complex, C-band, VH and VV polarization. If you use them, and as I said, if the distance from the satellite to the ground is changing, of course, the land should be moving. So that is what we are trying to detect. We call this interferometric SAR or differential interferometric SAR. Very nice areas of remote sensing if you are interested in reading, but very complex areas. Need great understanding. But remember, these are very interesting things in remote sensing. Without being touched with the ground, we are trying to get information about the ground in different perspectives. Now here, I'm trying to see how the ground is moving. Previously, I was trying to see flood. And also I was trying to see where the land covers are. I was trying to see what happened to the port city from 2016 to 2019. I was trying to see how the coast is changing. I was trying to see how the elephants are moving. I'm trying to see in Colombo, where are the hotspots where the people are gathering. How can I get that? By using secondary information about pubs, bars, streets. I can get them from satellite images. And I can imagine, I can initialize the social distancing measure, because the regions where the pubs and bars and their nightclubs are there, of course, the social distancing is going to go less than 1 meter down. So if I can give that into a satellite image and generate a map, of course, I can get the hotspots of Colombo, which are dangerously exposed to this disease. Right, so I had a talk for 1.5 hours almost. I hope that you got an idea about remote sensing. these are the references that I have put, and also if you need any information further regarding these things, please send me an email, and I want to thank SEDS for that. So thank you very much for listening, and Anupa, yeah, you can ask me questions, discussion.
Shall we move for the questioning session, and anyone can ask what you want to know about remote sensing and the space imagery. Please feel free to ask.
Well, then if you're not asking, I will ask you some questions, right? Let me see, there were some questions. Yeah. It was like, yeah. Sri Lankan in remote sensing point of view, there are real-time remote sensing data available freely like Landsat. Is there any necessity of manufacturing satellite cube or Pico for this purpose? Yeah, I think you guys are asking about these satellites that has been sent recently, right? I heard about Ravana and all. Actually, I'm not aware of these things much, but basically, if you send a small sensor up there, I don't think that you can capture very good images, right? That is the part that when I was doing my lecture, I stressed the fact that antennas should be very powerful, especially the transmitting and receiving antennas, and the antenna gain is very important. When it comes to microwave remote sensing, the antenna, there is a radar equation which is directly dominated by the antenna gain. So depending on the power of the antenna, the amount of signal that you record is going to get going to be in the image, because in radar, especially in microwave in remote sensing, what we record is backscatter, that is energy. That means how much of energy is coming per square meter back to the sensor. That is called backscatter. So this amount of energy coming back, depending on the polarization, as I said, if it is vertically polarized, it come and hit and goes back horizontally, you are going to lose the amount of energy. But if it is going to hit vertically and go back vertically, yes, of course, most of the time we will be able to get a lot of energy back, and we might be able to get a signature about the earth material down there recorded in the microwave domain, right? So the cross polarization and co-polarization both are there. When it comes to microwave imaging, there are no 7-8 bands, only 4 bands are there. VV polarization, VX polarization, HV polarization, and HH polarization. Only those 2. Okay. So polarization is the bands in microwave remote sensing, but when it comes to optical remote sensing, you know, of course, the spectral information, the number of bands says as the spectral resolution. So if I say there are 2 sensors, one has 10 bands, one has 20 bands, which one is having the highest spectral resolution? Very simple question.
The one with high band?
Yeah, 10 bands, right? Yeah, it is having the high spectral resolution. So we call the spectral resolution to be 10. That means if somebody says the data I'm using technically is having a spectral resolution of 10, that means you should understand that he's using a 10 band image. And so if I ask you, is there a relationship between spatial resolution and spectral resolution? Now, spatial resolution is the smallest amount of area that you can see from a satellite. Is there anything to do with the spatial resolution and the spectral resolution? Is there any relationship between them? Think about it. Of course, temporal resolution doesn't have any relationship with spectral or spatial resolution. It's completely orbital. And how many days it's going to go to come back to the same place? Temporal resolution. It doesn't have anything to do with this. But of course, you know, spectral resolution can have a relationship between the spatial resolution. Don't you think? Anybody? who has done remote sensing?
I think they don't, because the spatial resolution mainly depends on the size of the sensor. I mean, the size of the smallest part of the sensor, which can gather information. I mean, actually,
Energy.
the energy. Yes.
So you think that there is no relationship?
So far,
Yeah.
as far as my
The thing is, Puta, now if I say, if you can, have you now, when you go on working with remote sensing, you will find most of the high resolution satellite images have less than 5 bands. That means 2 centimeter or 0.6 centimeter resolution images. Most of the high resolution images doesn't have more than 5 bands. Why?
We cannot extract the energy from that.
Actually, the thing is like this. When you say 5 centimeter area, just imagine the amount of reflectance or radiance coming back from that region. It is very small, right? Right? Because it's a small area. But from 30 meter, there is large.
So I have a question.
Yeah. Tell me.
So when the resolution is higher, will that affect to the field of view?
Resolution is higher. Yeah, the field of view is getting narrow, right? That this the field of view is getting narrow when the resolution is higher. If it is become 2 centimeters, but if it is 30 centimeters, it is larger. Correct? Understand? Instantaneous field of view is getting larger when the spatial resolution is getting larger, like 30 meters. Correct?
Yeah.
Okay. Now tell me, the energy coming from a larger field of view is large, right? The energy coming from a large area is much more than the energy coming from a small area. Right? Energy coming from a small area is small. Energy coming from a large area is large, right?
Yes.
That is the reason why when energy is coming from a small area, what people do is that they occupy a large region of spectra in the electromagnetic spectrum to get more energy. So what happens if the satellite is working in the visible region, they sometimes combine whole blue region as one band so that you can get more energy. Whole red region as one band without dividing it, because even in the red region you can have different wavelengths, correct? Right? When I say red, it is not just one wavelength, okay? It's number of wavelengths. So large, the whole red region, right? And then they combine the whole near infrared region and short wave infrared 4 bands. They can't go more than that. They can't get a low spatial resolution and high spectral resolution. When there is low spatial resolution, it's low spectral resolution. Remember that. They are inversely proportional to each other. You don't have hyperspectral images of 2 centimeters. 196 bands with 2 centimeters, no, you won't get. You have 196 bands with 30 meter resolution. Yes, you have. Hyperion is there. But you have 2 centimeter 4 band worldview 2. 2 centimeter 5 band quick bird, 504 band, I'm sorry, but somewhere in there. Right? Cartosat 4 band, somewhere like 2.4, 3 centimeter. Understand what I'm saying? Think about
clear
it.
now, sir.
Okay? Kasun?
Yes, it's clear now, sir.
So there is a relationship between them. At the moment still, because you know why there is this, we cannot go out of this, because the sensors are actually passive sensors. They're not active sensors. We don't have problem with active sensors. They send their energy and take it back, so it doesn't matter how much of land cover it hit, because I send my parts and I take it back. I send the amount of energy and I take it back. So I don't have to depend on sun. And when it comes to active sensors, that means microwave. That's why there is no problem with this resolution, because in microwave sensors there is no such a thing called spectral resolution. Only microwave on the synthetic aperture radar, it is only spatial resolution and temporal resolution, and sometimes the radiometric resolution, but it doesn't also play a part because synthetic aperture radar images, DN values are not real numbers, they're complex numbers. So there is no like 2 to the power 16 bit, no, it's a complex number, JK. Okay, why? Because it records the phase of the wave and also the intensity. In the wave theory, if you want to record intensity as phase as a one number, you can't do it in real life. You have to do it in a complex line. So you have to go for complex numbers. When you go for complex numbers, complex theory, there is no such a thing called radiometric resolution. So most of these spectral resolution, radiometric resolution falls off from microwave sensors. Only spatial resolution and temporal resolution. And also, I said when there is huge cloud cover and 16 days, I don't have any way to capture an image. Of course, you can request the satellite provider or NASA or JAXA if there is a huge problem going on, like you know, there was Amazon fires. It came up last year and it was dreadfully going on. And then immediately Landsat, what they did is they captured on request, they controlled the satellite and captured the fire images. And also JAXA sent their Avenue 2 satellites just the purpose of capturing Amazon. So don't think that there is a fire at your home that the satellite is going to come and get pictures. This is Amazon, okay, talking about. So satellite moves and go and get pictures. They can't wait for 16 days because they won't know what is going to happen, because Amazon is like the lung of the whole world. Okay.
Excuse me, sir.
Yeah. Tushan,
I
how
was-
are you? You're safe, right?
Good, sir. Well, first I was
Morning.
small.
Good morning or good evening or
Yeah, it's still afternoon, sir.
okay, you just woke up.
Yeah, so like first I would like to say that this is great work and it's much appreciated, and like my warmest wishes, and I hope to see more events like this in future.
Thank you, Ishan.
So I have a small question.
Yes, please.
In the presentation, you showed the spectral signature of Earth features, like the turbulated water and clear water has a very low response.
Yes.
And this reef remote sensing seems quite interesting.
Yeah.
So if it's that low, how do you get the signatures from the reefs? Sorry, I don't have a remote sensing background, but
yeah, it's a good question, Shushan. Actually, in the case of that, you can see in the spectral signature, there is no spectral signature in reefs actually, because it's just subwater features. In that case, sometimes what we do is we try to remove, just like the cloud removal, we try to remove the water, right?
So you can do that.
Yeah, it's not successful yet. That's why this reef remote sensing came in, and there is a lot of work going on, especially with Landsat and the satellites that I showed you. It's very bit difficult to do the reef remote sensing, but there are some specific satellites like NOAA dedicated for ocean monitoring. And in that case, what they do is that ocean color is related to the health of the coral reefs. So it's like the secondary parameter that they are measuring. So that ocean color changes with the breaching of the coral reef, and therefore it is changing. Of course, there is a problem with the underneath reefs. So the marine biologists provide this relationship between ocean color on the ground with the reefs.
Excuse me, sir. Related to that question,
Yeah.
I have a bit another question related to the water column correction.
Yeah,
Uh,
water column correction. Yeah.
Yeah, can I have a basic idea about the water column correction? Because last few days I was struggling to do those things, but there were so many equations and
Yes,
statistical parameters, which is very hard to understand.
yes,
So
actually, there are few equations that is actually at the moment I don't have those equations, but of course I will provide you some reference papers that you can read about this, and also somebody did some water column correction with me a little time back. So maybe I will provide you some references and some notes on this. At the moment, Sashi, I don't have the water column correction because there are several equations that you have to do. The correction actually to remove the water content and to extract the what is happening at the coral reefs.
yes, sir. By the way, thank you very much for your nice detailed slides, and I encourage.
So the SEDS will go on, and this is the start, and we will go on talking about that. I didn't know you guys are there, otherwise I would have make some very serious detail.
But it is very quite interesting, sir. Very interesting and very useful. And
Yeah.
it was something like reminding me the throwbacks of my lectures. Actually,
I think I showed part of your research also in the.
Yes, of course, I can remember.
Yes, research, the flood monitoring.
Yeah, flood extraction. Yeah, of course. Sir, there is another question that is. That means you told about the models such as GPM, the global. How about the accuracy it holds for doing the academic things like researchers?
Very
projects.
good, Sashi, because as far as I know, there are a lot of academic community involved in this hurricane monitoring, and especially the volume, the measuring of the volume of the hurricanes. And they use the radar. Actually, it is K-band radar as far as I can remember, but I have not worked in the hurricane monitoring and all, but it is K-band I think they're using. Because it is low orbit satellites and they don't have to come back to the ground. So because of that, they are using K-band. And by using the top of reflectance and the bottom reflectance, they are getting a very good idea about the three-dimensional figure of the hurricane. And also the amount of water is actually because the K-band is sometimes not like the C and L band, they're trying to get the reflectance or backscattering from the water vapor and the water. So because of that also they can measure the amount of volume. If there is a large amount of water in that region, so they can get an idea of the amount of the volume of water in that. Based on that, that's how I have showed you that in the figure that they just make a 3D model depending on the value, the amount that they have recorded regarding the volume. Actually, it's the volume. In the case of these hurricanes and all, we don't have to be fine accuracy. We go for a fine accuracy because what we need is actually the amount of frequency in the changes of the frequency of the amount of water or amount of the cloud cover, the amount of dust, or in the hurricane. Actually, hurricanes happen mostly by the dust. Right. So they want to get the concentration level. So basically a distribution of the concentration, the varying of the concentration, not the direct measurement. You understand what I'm saying? It's like a secondary parameter, but that gives a good idea about the whole thing because it's a large process, the hurricane. But you can read about the GPMM, the precipitation measurement. It has been long from TRMM and providing a lot of data. So this is also part of remote sensing. It is not only imaging science. Now, because of this imaging sensor in this GPM mission, they can get a picture of the tornado and the hurricane itself as well.
Okay. When moving on to the Landsat 7, sir, the products after 2014,
Yeah.
like 2013, there is it is facing a
Stripping,
de-stripping.
This-
So is scanline error. So is there
Vertical
any
split.
method of accurate method in order to avoid those errors and to do the time series without any interruptions?
No, actually the satellites are planned for a period of time, because the vertical stripping actually Landsat happened in around 2000 level. It was started. It was not that severe when, like 2013 and 2014. I think it became real severe. That is the end of the sensor, because it is failing with its power consumption and all. So what we basically did is that we replaced the strip value with the adjoining vertical strips. That's what we did. Or otherwise, we ran windows that average up a particular region and assign a value for the place where the pixel DN value is missing. But normally when they say that it is the end of the process, that's why they launched Landsat 8. I think they are planning to launch Landsat 9 very soon. So,
Yes, of course.
so I don't know whether they have launched it. Maybe it is coming up very soon. Yeah. So at the moment, Sashi, there is no, as far as I know, in my personal view, I don't think that, because it's a complete vertical strip that it is dropping. So it's a bit difficult unless until the land cover is homogeneous. Of course, you have a chance to replace those values, because you really know that what that stripping line is representing, right?
Yes, of course. Thank you very much for your concise presentation and well as your comments. Thank you very much, sir.
It's good to see you. You're safe, right?
Yeah, of course.
You're safe. I think. I hope you are working on Landsat and Sentinel, right?
Yes, of course, doctor.
I'm hoping to see nice results very soon. Thank you for joining.
Thank you, sir. I encourage you all to do more statistical things, and I love to join for your statistical lectures too, because now I have the craviness and I now want to learn them more. Because I like to have a part of the statistical lectures.
Yeah, of course, because remote sensing is basically, it's not just looking at the images, you know that by now. It's a complete set of mathematics and statistics behind these images. That's why I showed you that for the younger guys who joining in, that's why I showed you that the power is in the matrix, not in the image.
Yeah, of course. Yeah, when we are going to do the projects, we just we should have a basics of these statistical parameters, and then
otherwise
we have to work
yeah. With remote sensing images.
Yes, of course. So I encourage you all to do some more.
I'll be contacting you guys all, Krishan and I think Sammani is back in Sri Lanka. And
yes, of course. I think so. Thank you, sir.
Yeah, thanks.
Thank you very much, sir. The examples you took were nice, because most of the people don't have the talent of teaching. It was nice.
Thank you, Krishan. Thank you. It's a pleasure. I humbly accept that.
So thanks a lot, sir.
Hi, Devinder.
Who is this? Hi, Ramesh.
This is yeah, this is actually, I don't want to waste your valuable time, because your students, they are asking very perfect questions. They are very lucky.
In my session?
Yes, from the start, from the beginning, I'm here.
No, Ramesh, and I just thought that only my students in the university is listening to me. If I know my batch gold medal list is here, I would have done. I would have made you.
No, don't say that.
How are you?
Actually, those people, your students, are very lucky to be there and listen to these type of lectures. Actually, we are not in this field of remote sensing. We are working in the other land survey part, so we are a little out of touch. But I just recall all those memories. It is very perfect.
I think you have better remote sensing results at the university than me, Ramesh.
No, very,
To
very.
be honest, yeah.
Actually, very,
You did very
very
well.
good, very good lectures.
Thank you, Ramesh.
Davinder.
Thank you very much. And Ramesh,
Yeah,
actually, just like me, I want my guys to get a lecture from you regarding construction and surveying and GNSS. I'll be contacting you soon, Ramesh. Okay?
Okay, okay,
Yeah.
okay. So we'll see about that. Actually, we hope to continue this one.
Yes.
I want to see more from you all.
Yes.
Okay, I don't want to waste this time.
No, you are not wasting. It's a pleasure, Ramesh, talking to you. Yes, we are going to continue, Ramesh, this, and we have to do that because
Yeah.
it was a requirement 10 years back, not now. Because we have been doing remote sensing for, and we have been doing surveying for a long period of time, but the country as a nation doesn't know what we really actually doing, right? So it's good that the thing came into online because of this pandemic, and everybody got into this Zoom and start talking. Otherwise, we would have been only lecturing inside the university. So see that so much of students that passed out and studying outside the university. Sushan is from Sweden, Sashi is from Dubai, and all are coming in, and more, I can see Dinesh also was there, one of my very good students, and I'm really happy to see all of you here.
Yeah. Actually, it's very perfect, but we need to upgrade our knowledge as well. So even though we are out of that session, that is the remote sensing, we need to upgrade it now. That's a good opportunity. Thank you very much to the society, and we hope to see more. Okay, Davinder, I just let other students to ask more questions.
Thank
okay,
you
see you, man.
Really, I'm honored to have these compliments from you, Ramesh. It's a great pleasure to listen to you. Okay, thank you very much for listening to me. Okay.
Okay.
Are there any questions?
There's one, but I'm not very sure whether it's related to this session.
It's okay. Go on. Go ahead.
I'm a pass out from CIS, Applied Science.
Okay.
I want to know that if we are doing a research, like image processing or something, what are the recommended sites to get images, satellite images?
Okay. Your name, Dua Nivarthan.
Nivartana.
Nivartana, you know my official email ID? Drop me a mail. Anybody in this session. So actually, I did not add the sites that where you can download the images free, but of course, I will I will send you that. Anupa, is there a way that I can send all of them these slides and all?
Yes, sure. We created a group
of the participants.
There are registered participants, about 303 participants.
Yeah.
I created a group with the SEDS
Sabra
email, and I can give it to you.
Yes, Nivantana, I will. I think you just drop me a mail, Dua. I will send you the link specifically for different sensors where you can download. Okay.
Okay. Thank you, sir.
So, if I may ask a question before we wrap up this session.
Yes.
So you said when it comes to microwave remote sensing, it basically is with the not the DN values. We don't have radiometric resolutions and anything. So it's based on complex numbers.
Dilanka, can you actually reading something? Dilanka, can you repeat the question, please?
Yes, sir. So when you said, I was a bit confused that when it comes to microwave remote sensing, we don't have really DN values, and it's based on complex numbers, right?
Yeah, DN value is a complex number.
Right. So then I was wondering whether we cannot do any graphical processing.
Of course you can, because you just imagine squaring up the real part and the imaginary part and adding them together. What do you get? You get a real number again.
Yeah, but I know that it can be done, but what I was thinking was mainly it is much convenient to use MATLAB or something like that. Or is that easier in doing other processing softwares?
Of course, Sri Lanka, if you go on to use MATLAB, you have to start writing the codes from scratch. But of course, there are some softwares that you can do the basic processing and get the image and do the one that you really want on that. Because the thing is, the preliminary processing, like, you know, as Sashi said, sometimes you have to do de-stripping. Sometimes we call this for Sentinel debursting or splitting, because there are several swaths. So you have to get what the swath that you like. Only that swath has the information that you want. So otherwise the image is very large, and if you open up in a small computer of your laptop, the laptop gets stuck because it's complex numbers, and these images, images are very heavy. So the initial processing you have to do in the software, maybe terrain correction till speckle removal and all those things you can do in the beginning from standard software. It makes much more quick your work. But then, of course, in the end, once you get the product, if you want to run one of your own models, then you can do that part in MATLAB or some other R or some other coding software. Even Python is very good for that.
Yeah, I get it, sir. That's clear.
Okay.
Thank you very much, sir.
So Bandula was there. Bandula, are you there?
Hello, sir. Very nice to meet you.
Hi, Bandula. How are you? Yeah, I know you are into hydrography. Your question I was just reading. It's good.
Yeah, I just joined to see you. Not much interest of this remote sensing.
Oh, Bandula, where are you now?
I wanted to see your lecture.
Thank you very much, Bandula. You are at the sea or you're?
No, sir. I just locked down in Qatar since 6 months now, and waiting to come Sri Lanka.
You're safe, right?
Yeah, it's okay. No problem.
Yeah.
Just now studying some stuff.
In your question, Bandula, you're talking about shallow water bathymetry. What actually are you using LIDAR for this at the moment?
Yeah. In Fugro they're using LIDAR, but we are not much involving on this stuff.
Yeah, actually the thing is, Bandula, at the moment there is no satellite data that penetrates the water to the level that you want. But of course, in shallow water, you can do a little bit with some of the blue band extensions. But basically, I think LiDAR is much more better because it has a capability of penetrating a low amount of water volume, not a very, very large amount of water volume. So I think, Bandula, you can raise this question to Dr. Sanka when he's talking about LIDAR, right?
Okay.
If you have time, just join in next month.
No, I'm in free right now, so I will be.
So please join in because he's talking about completely light detection and ranging. I didn't include that in my because it has to be talked separately. So you can raise that question, and also I'm interested in your question. I will have a look at this, Bandula, and I have your email address, and if there is some references, I will pass on to you.
Okay, sir. Thank you very much. See you in another one.
And please stay safe, okay?
Yeah. Thank you, sir. You too, everybody.
Any other questions from the audience?
There are other questions from Indula Karna Tilaka. So what is the difference between polar orbit and sun-synchronous orbits? Actually, polar orbits are sun-synchronous orbit. The name is sun-synchronous means actually it revisits the same place at the same time of the solar time. So we call it is synchronized with the sun. That is the name suggests. So if something is to get synchronized with the sun, actually you have to put it into a polar orbit. If you can't put it into a polar orbit, it is not going to get synchronized with the sun. That means at 10:30, when the sun is there, it comes and it images. If it is not synchronized with the sun, what happens? Satellite comes, sun is not there, and you can't image, and it has to wait till the sun comes. It's not going to happen. So sun is synchronized with the satellite. So all the passive satellites are synchronized with the sun. All the passive satellites go in near polar orbits or polar orbits. So geostationary orbits doesn't have the sun synchronous capability, because it always goes like the it's a shadow of the Earth. Just like my shadow goes with me, it goes in the same place. Okay. Can we see a certain person from satellite? Yeah, this is very good, because sometimes with the Cartosat and the QuickBird, you might be able to see person, but not whether he's black or white and all that is not there. You can't do it from outer space, but there are low orbit satellites which are not basically exposed to personal use, but for military use. Actually, the satellite sensors that's available for us for our commercial purpose, we don't have the capability of seeing a person. But I know if you use QuickBird like 0.3 centimeters and not placed in, you can't do. With spot 6 or spot 7, most probably you might be able to count the number of people. Nivartana, I will send you the links. Okay, thank you. Can we see a certain person? I think I have answered that question. USGS, yes. This USGS, Shan, you have posted the USGS GOV. There you can get a lot of satellite data downloaded. And also, if you go to European Space Agency satellite portal, you can download all the Sentinel-1 and 2 data freely. And also, at the moment, ISRO has not provided, Indian Space Research Organization has not provided us free data. So these are the two sites. Some more sites are there. I will just pass. If you can, if you are really interested, just drop me a mail. I will pass you those links. How future of remote sensing in Sri Lanka? There is no present actually. So in that case, I cannot say what is the future is going to be like. So actually, I wish that the future is going to be better. But basically, at the moment, the present remote sensing in Sri Lanka is also a doubt. Is there any satellite images which accurate height values for road design? Accurate height values. Yeah, actually, I showed you a part of interferometry in the end. Basically, if you go on this process of differential interferometric SAR and convert this interferogram into a digital elevation model, of course, you will get a very good height values, right? And the case is that there are different wavelengths in synthetic aperture radar, like L-band and C-band. C-band is shorter than L-band, so in that case, C-band does not come through the canopy and hit the ground. But L-band, the JAXA, all Japanese satellites, especially radar, they are working only on L-band, and the most useful band in synthetic aperture radar is L-band. But it doesn't have a good spatial resolution, but it hits the ground, it goes through the canopy, and it always map the surface. It doesn't map the canopy surface, it maps the terrain model. It can create the terrain model, right? So because of that, if I create a 3-dimensional model using this L-band interferometry, of course, I can get good height values for road design and all. I think in Japan, most of the time they use these digital elevation models generated by JAXA phase array type L-band synthetic aperture radar pulsar to satellite data, radar data, in order to generate the surfaces for road cross sections. So interferometry is the art. I did not talk about interferometry. Of course, I would like to dedicate one lecture more completely on synthetic aperture radar if you guys are interested. Satatan, thank you very much from IIT Katnaika. I'm really happy and it's a pleasure and to have you guys all here, my students from IIT Katnaika. It's a pleasure to have you guys here, and I hope all of you are doing good. Yeah, Nuanti, you can use the Alaska satellite facility for Sentinel-1, and also the Sentinel data hub you can use. Kavinda Viswajit, Kavinda, thanks for the question. So, do Sri Lankan use this remote sensing techniques? Not much. Actually, the agriculture department requested me to provide flood in Kilinochian area, because there was a request from the agriculture department that they have to pay for the damaged paddy fields, but there is no way that they can identify actually the claim is right or wrong, because people come and say my paddy field is gone for floods, and there is no way that they can determine whether there was a flood in that paddy field or not. So they have to just pay everybody. It was a huge amount of money. So the agriculture department came to me. That's why I showed you some of the flood, and they agreed about the results that I provided them. But unfortunately, at that time, this project was involved with some other people. I'm not going to comment on that, because there were two other great universities involved in this project, but unfortunately they did not use synthetic aperture radar data. They went for optical data, and they found there is total amount of cloud cover, and they reported the president that these satellite data cannot be used, and unfortunately that had happened. And after that they came to me, but unfortunately COVID also came with that, so I couldn't do much more about that. Dinesh, thank you, Dinesh, for the comments. There any possibility to take space garbage with current space missions? Of course, there might be possibility with the LOs that I showed you regarding the wind, right? I don't know much about that satellite, but I'm really interested in first instance it was sent. I'm still looking for getting free data from LOs, because wind is something that I was fancy about from my childhood, something that I really love personally. So anything that models wind interests me. So that whole project from ESA, it's done by European Space Agency, not by NASA. So I am very interested in that. And if you can detect the wind surfaces, of course, that technology can be transferred in order to detect space garbage, because if you send a radio pulse, of course, if it's garbage, or that you can get a signal back, then by that you can map. But the problem is actually, you have to be very, very sure that it came from metal or asteroids or some other particles. Because when you send a radio pulse, the problem is that you get a signature back, but you don't have a spectral signature. So you can't segregate metal and asteroids or particles or water vapor, because there is no spectral signature. The energy goes and it hits the target, illuminate the target, and comes back. We call it backscatter. Then what you have to have is some sort of a reference that it was metal. In the ground, we have radar cross section for metal. Just we keep some metal structure. The radar satellite passes, we get the satellite image, and we know the cross section. That means if a radar pulse hit, how much of it get illuminated and how much it is going to go back. We can measure that on the ground. So we know that we can measure it with the satellite and we can compare. Because the metal structure is on the ground, we can do that. But something on this outer space, it's harder to get the actual radar cross section calculated. Just I hope you understand what I'm saying. It's like matching something on the ground with the satellite data, just like your spectral mapping, right? But in this case, the garbage is not on the ground, so it is in the outer space, and how to get the cross section of the outer space elements is the problem. We don't have a database for those kind of elements, because it might be 30 kilometers up there, or 40 kilometers up there, 50 kilometers up there. When its altitude is changing, its radar cross section is also changing. So there should be some way that we can get a measure of that. That is also a very good question. And coming another question: how vegetation can be green if we can apply RGB into false color composite as we like? Just simply just apply it, just go with the green band to green, put the green band to green, red band to red, and blue band to blue. Don't put any infrared band. You will see the true color composite. It is called true color. true color composite and the false color composite. Most of the time I use false color composite because in radar, in the remote sensing literature we like using false color composite. My practice was using false color composite, but if you put true color composite, directly use R into that without putting near infrared, you will see the true color composite, and because of that you will see green green, blue blue, and buildings brown. Okay. Dinesh, I use software called Plex for getting Google Earth images with elevation values for design, but elevation accuracy is low. Please can you let me know, is there any other software can we use? Dinesh, at the moment, Dinesh, actually I don't know. I'm just curious about this use of Google Earth in for your height values. I know it's good, Dinesh, that you are always aware of the accuracies. As I know, you're very much concerned about the accuracy. Please be concerned about that, because these elevation that you get from Google Earth will not be very reliable. Please can you let me know if there are any other software we can. No, Dinesh, at the moment I really don't know any software that can extract height from Google Earth. I can give you softwares that can extract features, but the height, that is, Dinesh, I really don't know at the moment. I personally am reluctant to use Google Earth to get height values, because I have been in the construction field as also, and in the case of water projects and the projects that you are involved in, Dinesh, I think the height is very useful and very should be very reliable. So please be careful in that sense if you are using that. But I will have a look, Dinesh. This question is in my mind, and yeah, I should note it down. You use Plex, right? Yeah, Dunendam, thank you. Yeah, thank you, Janit. Thank you. I hope you are doing good in Rwanda, and I wish you all the very best, and please be safe, Janit. Okay. Yeah, Tilan, you're asking about air pollution using remote sensing. Tilan, it's a separate thing. Could you please drop me a mail? There is a possibility by using MODIS aerosol optical thickness. It is something different from the reflectance. So by using aerosol optical thickness, actually it is the moving aerosol particles that get reflected by MODIS moderate resolution radiometer. So it is possible for you to get a glimpse of images of air pollution, but the problem is if you are really interested in PM10 or much closer value particles, then you have to go in detail study, because this has been used MODIS has been used to map PM10, the PM10 and that order particles, but actually is it the thing that is causing air pollution has to be concerned. So there is some sort of fine line between these two. So in that case, Tilan, please drop me a mail regarding this. I will send you some of the papers that has done air pollution modeling by MODIS aerosol optical thickness. I think I have answered that. Thank you, Dinesh. Yeah, thank you, Das. Thank you very much. Charit Marushankar, I'm going to very colorfield. Yeah. I saw this question. I somehow missed it. Colorfield concentration in Kotmale River to derive remote sensing reflectance. I'm going to use CRT algorithm in SNAP, but it didn't use radiometer to derive in situ radiance at the study area. Is it okay, sir, to use band ratio as a predict the concentration of? Yes, you can use band ratio, but actually you're from Javadanpura, Charit. Thank you for the question. It's a very good question, Charit. I think you are using band ratio, but do send me a mail if you can writing which bands you are going to do the ratio on, and then only I can say what is going to happen to the spectral reflectance. I wish you had some sort of a ground spectrometric information. If you had that, it would have been much more better, because you could have matched the chlorophyll spectral reflectance with the spectral reflectance that you get from the satellite image after the atmospheric correction, and you can match them, and you can map the chlorophyll content. So please let me know which in detail, please, because this is a detailed answer and a detailed understanding. So please write to me which bands you are trying to ratio, and a little bit detail in your study, so that I can help you out. And it's my pleasure to help you out. You're a master student at postgraduate at Jawaharlal. Please do write to me, okay? Yeah, Anupa, it's been like I couldn't bring my water bottle.
Sure, sir. If the audience have any problems, we can wrap up now.
Yes, I think it's okay, because I think we can have another session, because there is large amount of people interested in this. So maybe by taking on the areas that, especially the shallow water bathymetry, Bandula and Chushan both talked about that, and Chushan also talked, and Sashi also talked about this reef remote sensing. I can directly dedicate, and also this chlorophyll case coming from Javadhanpura. I can all related to water, and I see the interest in there, so I can dedicate one other lecture again regarding these applications, and especially the remote sensing images that can be used for these kind of purposes. And I'm happy about these questions, because I did not expect to have this in-depth discussion, but I'm really pleased, and I'm really happy, and I'm really humble to be here and talk with you guys. Yeah, Bandula, thank you.
Okay, thank you, sir, for your valuable speech on remote sensing and helping us to organize this event. And I would also like to thank Madam Nanmali also, great support to organize this and start this webinar series.
Yeah.
And thank you all who joined with us today in this webinar session. And tomorrow is the second day of the webinar series. Look at the environment of Earth from spatial science perspective. And I would like to make this time to invite you for tomorrow lecture also. Maybe meet tomorrow.
Okay, Anupa, shall we wrap up the session, because it is like almost.
Okay, sir. We can wrap up now. Thank you, sir.
Thank you very much, Anupa. And I have to say, Anupa, you put a lot of effort in making this event, and credit goes to you, Buddha, okay? Because of you, actually, I got into this year because of your continuous request and all. And I appreciate that. And without you, this would have not been possible. And you have put a lot of dedication and effort, Anupa, and I really appreciate your service, okay?
Thank you, sir.
Okay, then bye-bye, and everybody please stay safe, because you know, that's things are not very safe. So we are under a pandemic, so remember, keep safe, keep your hands very clean, and stay safe. Bye-bye.